Hello, this is MAT221, Calculus 1. This is Mrs. Johnson. We are in section 4.3 and we are talking about in the last video this particular example. We tested using the first derivative test and we found that at x equals -2, the derivative changed sign from a negative value to a zero value to a, from a positive value to a zero value to a negative value around x equals 2. And by the first derivative test, if the first derivative changes from positive to negative, then we know that x equals -2 is locating a local maximum value on the curve. Over here at x equals 4/3, the derivative on the left side of 4/3 was negative. The derivative on the right side of 4/3 was positive. The derivative was changing sign from negative to positive around that critical point. Therefore, x equals 4/3 located a local minimum. Now, to find the actual value of the function at those points, we put x equals -2 and x equals 4/3 into the original equation to come up with the actual maximum and minimum values. Now, again, we can do those on a calculator or a computer, or just substitute those values into the original function. So this curve has a maximum, a local maximum of 17 occurring at x equals -2, and a local minimum of -41/27 at, at the x value of x equals 4/3. Okay, so now let's do another example, but this time let's use the second derivative test to determine the extrema of the following function. So let's take the first derivative and set the first derivative equal to 0. Now again, a lot of times with this, we can't remember how to factor well. I factored out a 3 here and then factored again. We often will be able to use Mathematica here to have Mathematica solve those for us to solve where the first derivative is equal to 0, and we'll be doing that in class, as well as some other videos. So I have critical points at x equals 8 and x equals -2. So our procedure for the second derivative test is, first we find the first derivative. We set the first derivative equal to 0 to find critical points. We find critical points. Then we take the second derivative of the function and we put each critical point into the second derivative. So I put the critical point of 8 into the second derivative. I get a positive value. I put the critical point of -2 into the second derivative and I get a negative value. Okay, so what does that tell me? If the second derivative is positive at x equals 8, that means the curve is concave up. And if the curve is concave up, the critical point's got to occur at the bottom, so that would be a local minimum. When x equals -2, the second derivative was negative, which means the original curve is concave down, which means the critical point is going to be at the maximum point on that concave down region. So because the second derivative is positive at x equals 8, therefore the function must have a local minimum at x equals 8. And when the second derivative at x equals -2 is negative, therefore f of x has to have a local maximum at this value. Now in that last example, I should have really gone further and to actually find the actual values of the curve, where I could take those values and put them back into the original function. So, does this function have any points of inflection? Now, this is the third test that we talk about. This is called the test for concavity, or the concavity test, sometimes called the inflection test. The inflection test, what we do is we take the first derivative, then we take the second derivative. And we don't care about critical points in this test, but we do care about key points or possible points of inflection. Possible points of inflection occur when the second derivative is equal to 0. Solving, we get a possible point of inflection at x equals 3. What we do next is put a number line with that value on the number line, which divides the number line into two pieces. That piece that is less than 3 and that piece that is greater than 3. And we test the second derivative using this. By the way, we're using the second derivative, but we are not using the second derivative test. The second derivative test tests for local extremes. This test that we're doing now is called the concavity test, or test for points of inflection. It uses the second derivative, but is not called the second derivative test. I put in a value here. I tested 0 because that's an easy value to put into the second derivative, and I get a negative value. That tells me the curve is concave down from negative infinity to 3. And then I test above 3, I tested 4, and I put it into the second derivative. I got a positive value. That tells me that the curve is concave up from 3 to infinity. That means x equals 3 must be a point of inflection, because by the concavity test, the second derivative is changing sign around this key point, or around this possible point of inflection. So a point of inflection occurs in this function at x equals 3. Lastly, for this part of the unit in section 4.3, we're going to talk about the mean value theorem for derivatives. Now, there are several worksheets also that you can work on in the Blackboard folder for section 4.3 that works on the first and second derivative test and the mean value theorem. The mean value theorem for derivatives says this: if f of x is a differentiable function over a closed interval from a to b, then at some point between a and b, this equation will be true. All right, so let's try to think through this equation and see exactly what it's saying. Well, first of all, differentiability is implying that we must have continuity. Differentiability is even more potent than continuous because I can't also have any cusps, I can't have any sharp corners, I have to be differentiable function. So if I have a differentiable function over a closed interval, I have to have those two hypotheses in place to use the mean value theorem. Then what is the mean value theorem saying? It's saying this is equal to this. It's saying at some point C between A and B, the average rate of change, which is what this side is, this is the slope formula, the average rate of change between A and B, the average rate of change is equal to the instantaneous rate of change at x equals c. Now, why is this called the mean value theorem? Because this is the average, notice average rate of change. So the average rate of change is equal to the instantaneous rate of change. So that's why it's called the mean value theorem. The average rate of change and the instantaneous rate of change are equal to each other at some point in the interval from A to B. So the mean value theorem is saying at some point in this closed interval from A to B, the actual slope equals the average slope, or the instantaneous rate of change at x equals c equals the average slope between A and B. I like to look at things in pictures, so let me show you what this looks like in a picture. If I said that this is points A and B, this line would signify the slope between the endpoints, between A and B. So the slope of this line would be the left side of the mean value theorem equation. This chord, this line, tangent line to the curve, is parallel to that chord. In other words, their slopes are the same. And notice that would be the instantaneous rate of change at x equals c. So what this mean value theorem for derivatives is saying is somewhere between A and B, there's a tangent line that is parallel to the slope of the chord, or parallel to the chord passing through the line that passes through the endpoints. So the average rate of change between the endpoints from A to B, there's a point somewhere between A and B where the tangent line to the curve will be parallel to the chord joining the endpoints of this interval. We know that two lines that are parallel have equal slopes, so they will be equal to each other. So show that the function f of x equals x squared satisfies the hypothesis of the mean value theorem on the interval from 0 to 2. Then find a solution for c. Well, first of all, we know that x squared is a continuous function that is differentiable everywhere, and especially on the closed interval from 0 to 2. So I have a closed interval and I have a differentiable function. Therefore, the hypothesis of the mean value theorem must exist. The endpoints of this interval are at 0, 0, and 2, 4, because I put 0 and 2 back into the original function to find those endpoints of the interval. So that means somewhere between 0 and 2, this must be true. So I'm going to put in my values here. B was 2, A was 0, and the derivative of x squared is equal to 2x. So the derivative of x squared at c will equal 2c. Finding this from the equation that was given, f of 2 is equal to 4, f of 0 was equal to 0 because 2 squared is 4, 0 squared is 0. Remember the original curve, the function was x squared. And the derivative at c would be 2x, so the derivative at c, would be equal to 2c. Solving for c, I get c is equal to 1. So that means the tangent line to the function f of x at x equals 1 must have a slope of 2 and must be parallel to the chord joining 0, 0 and 2, 4. This ends this PowerPoint session for section 4.3, but please make sure you go into the worksheet folder and work on some more of the worksheet problems on the mean value theorem and the first derivative test and the second derivative test and the test for concavity. Have a great day.